fed a piece of meat, it may take a full week to reopen. Seen in time-lapse photography, the trap plates press tightly together. Digestive juices are secreted onto the meat and can be seen at the bottom of the leaf. The result is most dramatic. A good meal, and there is a sudden and amazing burst of growth. It's this ability to digest flesh that enables the Venus flytrap to gain the precious nutrients on which all plants thrive. Although one fly may escape, sundews are among the most sophisticated of all death traps. Two ants find their way onto a longleaf sundew. Ant number 1, attracted by the sundew's color and the scent of its sugar-sweet droplets, is getting a hearty meal. Now the ant has discovered its danger and makes violent efforts to free itself. For its size, it's very powerful, but it's fighting against one of the strongest glues in nature, controlled by a plant that responds to every movement of its prey. The ant twitches in its death throes, but already the sundew has released digestive juices. The plant has begun to absorb nourishment from its victim. To help with absorption, other tentacles curl inward to envelop the ant. In this longleaf species of sundew, only the tentacles move, but here we see a roundleaf sundew closing on a mosquito. In this case, the leaf itself curls round in its embrace of death.
Plants also exhibit rhythmic movements similar to those in an animal's heart. In some plants, the pulsations can be visually observed, while in others, it can be detected only through electrical devices. The upward and downward movements are recorded on this smoked glass plate. Similar curves are obtained by recording the movements of a frog's heart. When poison is dropped on a leaf, the plant gives a death cry, and its pulsatory movement stops. Excitation, brought about by a stimulus applied at a point on the plant, is transmitted to other parts of the plant. The same thing occurs in an animal's body. When a child puts his finger in a flame, before he has time to cry out, the arm is automatically withdrawn. This is because an ingoing strong stimulus reaching a nerve center is reflected into an outgoing impulse through a new path, causing the hand's withdrawal. A similar reflex arrangement has been discovered in the mimosa plant. The excitation due to a stimulus applied at one end of the leaf first reached the main palvinus and then is reflected back to the other leaves. Observing the world of plants, he used to say, "They are our mute comrades whose life runs its silent course. They record their reactions without sound, but our eyes can see the stirrings of their life and the pangs of their death."
324 fellows of London's Royal Society. In the same hall where Darwin, Huxley and Faraday made history, The learned gathering listened with polite interest as the obscure Indian scientist described his pioneering measurements of radio waves. The object of his future experiments was to prove through the design and use of highly specialized machines that all the characteristic responses exhibited by animal tissue are also to be found in plants. The Bose experiments were denied publication by the Royal Society. By daring to suggest that plants have a sensory system similar to humans, Bose offended the learned members.
And now the strange story of the evolution of death traps reaches an even stranger ending. Or is it a beginning? The seed of a shepherd's purse has fallen, future generations dormant within. As if a prelude of perils to come, seeds immediately attract the attention of hungry creatures. The vast majority of all seeds that reach the ground are fated to be devoured by animals. But the shepherd's purse has evolved a mechanism to beat the odds. Its seeds attract soil creatures, but then they immobilize them with slime, kill and digest them. The delicate seedlings that emerge are fortified with a banquet of decaying worms and mites. Their first battle over.
Plants have been known to respond to sound in general, but two University of Missouri scientists recently discovered that they react to caterpillars' chewing noises in a very specific way.
When they were attacked by caterpillars, they responded with much higher levels of these mustard oils that are toxic to caterpillars.
To make sure the chemical reaction was incident-specific, the scientists set up an experiment. After establishing their constants and variables, they put a caterpillar on a type of small flowering plant. They took leaf movement measurements and made audio recordings as the caterpillar fed and then tested the plant's leaves. In the next stage, the plants were split into groups and each was introduced to a variety of noises and vibrations. Some replayed the recordings while others got sounds and tremors of other insects and rustling wind. One group was left in silence. Only the ones that had listened to the caterpillar recording were quicker to react when the pesky creatures were reintroduced. The scientists aren't sure how plants pull it off, but do plan to conduct more experiments to get to the bottom of the mystery.